everybody, this is Alberto Marquez, and this video is a 4 video on simulation inputs. We are going to discuss how to transform uniform random numbers into different random variables with the desired distribution, probability distributions as we wish. The generation of random variables is important because we want to be able to represent reality in our system based on the experience of what's happening in the reality in our system. We want to be able to translate that randomness in an equivalent fashion when we are trying to depict how the system behaves. That includes, most traditionally, time between arrivals and service times, but it also could have description of other type of random variables like the size of the order, the amount of tonnage that is carried in a vehicle. It could be downtimes that happen in equipment or even personnel that is not available every so often. So all these randomness affect the performance of the system and should be taken into consideration. So while we can gather the data that represents the behavior of the system on one hand, now we should be able to generate equivalent random variables that simulate the behavior of the system. The first idea on how to achieve this is what we call the inverse transform. The inverse transform is a methodology in which we use the cumulative distribution function of a random variable. Remember, these are the functions that go from 0 to 1 in the value of the function. For instance, in this case, we have here represented a uniform distribution for which the cumulative distribution function translates into a straight line. If we have this cumulative distribution function, we can map backwards from the function back into the domain, in this particular case in the range from A to B, an inverse. So we can map from the random numbers generated from 0 to 1 into the variables that would have generated that probability. In other words, we can map from Y into generate a variable X that falls between A and B. There are different type of solutions that we can approach in order to use this type of inverse transform. One is analytical for when the function is easy to compute. Another one is table-based for when the cumulative distribution function is a little bit more complicated. And finally, we could have a numerical solution. In some cases, it's a combination of analytical and table-based implemented in a numerical way. So let's consider the analytical inverse for a uniform distribution. The cumulative distribution function for the uniform is defined by x minus a divided by b minus a. And when we do the algebra, and what we do is we make r the function x, because that's the number that is going to fall between 0 and 1. When we compute the inverse of r, now we solve for x and r becomes a parameter. When we do the algebra around to solve x, we have r times b minus a plus a equals x. The analytical inverse for a triangular distribution. Triangular distributions are very popular in simulation because sometimes we don't have a lot of data. We could have the minimum value that the random variable will have, and here depicted with A, and the maximum value that the random variable may have, depicted here with B, and the most likely event, here depicted with C. So when we have these, the function is defined depending on the domain. If x is less than or equal to a, the function is 0. If x falls between a and c, then the cumulative distribution function is x minus a squared divided by b minus a times b minus c. If x falls between c and b, now the cumulative distribution function is 1 minus b minus x squared divided by b minus a times b minus c. For any moment where b is less than or equal to x, then the cumulative distribution function is already 1. And if that's what we have, we can solve for the most important ranges, which is between when x falls between a and c, and when it falls between c and b. And the expression that we have is that the inverse that allows us to compute the x will depend on which value we want to have. We need to select the corresponding r for which of these two variables to use. And for that, we can just find where these two lines meet. The expression that we have for the inverse is a function of the random number and will yield the value of x. We can see from the graph of the cumulative distribution function that the critical value for r that will define which of the two functions will be used is the value of c minus a divided by b minus a. If the random number is larger than that, it will use the inverse for the ranges between c and b, and if the random number is less than that critical value, the inverse that will be used is corresponding to generate random numbers between a and c. Another analytical inverse is the exponential distribution. The exponential cumulative distribution is of the form 1 minus e to the minus lambda x. So when we equal that to the random number and we solve for x, the expression that we get is negative natural logarithm of 1 minus r divided by lambda. Now it happens that 1 minus r is a uniform random number just as well as the random number itself, which is also a uniform random number between 0 and 1. Therefore, we can simplify the expression. Instead of having negative logarithm of 1 minus r over lambda, we can rewrite that as negative natural logarithm of r over lambda. Sometimes we have discrete empirical data, and the easiest way to do this is by means of a table. If we have, like in this example, a discrete probability distribution for the possible values of a random variable, a discrete random variable, and we have different values for that probability, 25%, 15%, 18% in this example. What we could do is we can generate the cumulative distribution function or the cumulative mass function for this random variable. And as we do that, we generate a pattern that allows us to make a map on what should be the output of the random inverse. In other words, once we have this, and now it's easy to see that if we have a random number between 0 and 25, we should get 1. If we get a number between 25% and 41, or 0.25 and 0.41, then variable will be 2. If we get a random number between 0.41 and 0.58, the random number we will get will be number 3. We need to manipulate this through the logic of the computer, and the easiest way is to just have tables. The binomial distribution could work in a similar way. We can compute the binomial distribution, which is expressed as the combinations of k elements into n, k successes into n attempts, p to the k, 1 minus p to the n minus k. In this example, n equals 7 and p equals 0.35. The full domain is expressed in the table, both for the particular probability of having exactly that number of successes and the cumulative distribution. Once we have the cumulative distribution, we can make a map. Depending on the random number that we get, we would select that value. So for instance, if the random number is 0.7, then what we would have is that the probability of having x being less than or equal to 3 is 0.80, so x potentially could be 3. We check with probability of x being less than or equal to 2, and that's already too low, 0.5323. So this number fluctuates between 2 and 3, and the right solution to have is to select k equals 3. And this is how it looks like when we do it. Sometimes we could have a continuous distribution in which we have no parameters. We only have a histogram. And in this case, we work a similar solution based on tables, but our tables will connect segments of lines that will generate the cumulative distribution function by means of connecting the frequencies that we're familiar with. So, for instance, if the range between 20 and 30 has a relative frequency of 27, then random numbers generated between 0 and 0.27 should be ascribed to that range between 20 and 30. If for the range between 30 and 52, the relative frequency is 10, then for that particular range, we should add 10%, and therefore that means that random numbers falling between 27 and 37, 0.27 and 0.37 would generate random numbers in that particular range. In a similar fashion, in random numbers, if for the x variable to fall between 52 and 58, the chances are 30%. 30% added to the 37% prior obtained means that random numbers generated between 0.37 and 0.67 should fall in the range between 52 and 58. And in a similar fashion, we can compute the others. Once we have the segments of straight line, we can anticipate the slope and the intercept. And we can compute those based on the fact that we know the points. And once we have those data, if we generate random numbers, then we can map these values. For instance, if the random number is 0.1, the slope is 0.027, the intercept is negative 0.54, and the corresponding value, by doing the inverse of the straight line, we obtain x equals 23.7. If the random number is 0.35, we use the next slope, which is 0.0045, and the intercept now is 0.1336, and the corresponding x is 47.6. If the random number is 0.5, the slope is 0.05, and the intercept with the vertical axis is negative 2.23. So at 0.5, the value of x is 54.6. In the case of a random number being 0.7, then we obtain 64 as a response because the slope is 0.0050, and the intercept is 0.38. Finally, and for the last range, if we would get a random number of value 0.85, that would map to a value of 76.4 for the random variable, due to the fact that the slope now is 0.0417 and the intercept is negative 2.33. There are other methods that we could use, which are, for instance, the convolution method. The convolution method adds random variables, and when we add them, they actually change the distribution shape, and in such a way that, for instance, if you add random exponential with the same lambda, you would get an Erlang, and then depending on the number of exponentials that you add, you would get an Erlang of k value, where k is the total number of exponentials that you added. We also can generate chi-square distributions by adding normally distributed variables that are squared. And finally, we can generate a normal distribution or a quasi-normal distribution if we just simply add 12 uniform random numbers and subtract 6. This is an example where actually it's a t-student distribution, but we can use it for purposes of almost being normally distributed. And this is how we do the inverse and other methods on how to generate these random variables, and we will continue with other more advanced topics on simulation.